Hello everyone. In this video, we are going to discuss about the DAG representation of basic blocks. DAG means it's a directed acyclic graph. So basic block contains a list of three address statement. To represent a basic block, we can construct directed acyclic graph. So with the help of this, we can identify the common sub-expressions. And in a DAG, all the leaves are used for representing variable names or constants, and the variables are initially used, means it should be subscripted with 0 because some other time it can be replaced by other values. So initial values means it should be represented with the subscript 0. Then all the interior nodes represent operators, and internal nodes also represent result of the expression. For example, consider the statement, three address statement x equal to y plus z. DAG means it is used for representing a basic block. So assume that the basic block has only one statement. So y plus z means interior node is operator. In the as per the second rule, interior node is operator, so plus, and leaves are its left child is y naught and right child is z naught, because y and z are the initial values, so it should be subscripted with 0. So y naught and z naught are the left and right child for plus. Then result must be indicated in the internal node. Here the result is x, so this plus is indicated with x, identifier x. Now we will consider another example. Here our basic block has four statements, four three address statements: a equals b plus c, b equals a minus d, then c equals b plus c, and d equal to a minus d. So DAG means it will consider statement by statement, each statement in turn. Okay, so first take a equals b plus c. So the DAG is constructed by constructing plus, and whenever we are creating a new node, we have to check whether that node is already available or not. If that node is already available, then there is no need to create it, that node. Simply we have to attach that identifier as a list of identifier. For example, suppose another statement called a equals y plus z, then this plus, the operator plus with y and z are already created, right? So that a must be attached. For example, a equals y plus z means plus y z is already constructed, so we have to just attach a. Is a attached identifier list. In this list we have to attach a. Okay, so first we need to construct plus. Plus is not already constructed, so first plus, and its left child is b, right child is c. These are the initial values, so b naught and c naught. And what is the result of this node? A. So it should be attached to the internal node. Next we need to construct a minus d. So we have to check whether minus, the node minus is already there or not. No. So minus should be created. Its left child is a and right child is d. So left child is previously constructed node. So this a, the child is also already computed, so that it is the left child for minus. So for the node minus, left child is a, right child is d, and d is the initial value, so d naught. And what is the result of this expression? B. Then we have to perform b plus c again. So we need to check whether plus is plus, the node plus is already created with the b and c. Now the most recent value for b is this one. So from this there is no node constructed, no operation for b plus c. So we need to construct it again. Plus, left child is this b, right child should be c naught, right child is c, right? So this c is not re-evaluated anywhere, so this should point to this c. Now the result of this expression is c. Now c is changed. Hereafter is c, if c is participated in some other computation, we have to use this c. This is the most recent value for c. Okay, then final value is a minus d. So minus with a and d. Here A and D are not evaluated after this. So A and D values are this one only with the interior expression minus, okay, operation minus. So minus A comma D. So this node is already constructed, so that simply we have to attach D to this node. Okay, so here B A minus D and this A minus D. Second and fourth expressions are common sub expressions. So that is identified and we didn't create a new node for this. Okay, so this is the DAG for this corresponding example. We will see another example also. Now consider the second example. So we can construct DAG for the first expression B plus C. So the operator is plus, its left child is B, so it's a leaf and it's an initial value, so B naught, and its right child is C, so C naught, and the result is A. Now B minus D. So now B minus D should be constructed. So minus is a new operator, so we need to construct it. So minus is a internal node, its left child is B, so it is already available. So there is no need to give another node, we have to use the same leaf, so B naught, and the right child is D. D is a new value, so D naught, and the result of this expression is B. So hereafter if we want to refer B, we have to use this B, not the initial value B naught. The next expression is C plus D. So plus, it is also not already available, so plus is a root, its left child is C, so this initial value only, and right child is D, so this D, and its result is C. Now the final one is E equals B plus C. So now current value of B is this one and C is this internal node. So plus is an operator, its left child is B, right child is C, and this result is E. So this is a DAG for this particular basic block. So for this third example, first we need to compute minus C, unary minus C, then B star U minus C, then this minus C, then B star minus C. Then this must be added, then that value should be assigned to A. Here from the expression we are going to construct the DAG directly. So here the minus is a internal node, and it is an unary minus, so it has only one child, so it's C, so we can write it as C naught. Then B star minus C must be performed, so internal node is star, its left child is B and right child is minus C. Then we are going to construct B star minus C, this one. So this is already constructed, so there is no need to construct the same subtree again. Then we need to perform plus operation. So for the plus, left child is B star minus C, right child is also the same subtree. So we need to construct DAG like this. Then the entire expression must be assigned to A. So now the operator is assignment and the left child is A. So this is another way of constructing DAG. From the expression, without constructing the 3 address code, directly we can construct, or we have to construct 3 address code. Then we need to take each statement in turn and we have to construct the 3 address code. Now consider this example. So this example is given in the textbook, and this example we have already seen in the basic block and flow graph. So this is the basic block 2. Okay, so this basic block has 10 instructions. Now we are going to construct a DAG for this sequence of 3 address instructions. So first we need to consider T1 equals 4 star I. So star is a node with the left child 4 and right child I. So I naught. Then A of T1 must be performed. Indexed assignment statement. So A of T1 must be performed. And what is the result of this? T1. So that should be attached here. Next we need to perform A of T1. So here the operator is indexed, the in array symbol, and left child is A, right child is T1. So T1 is a right child and the operator is operator is the array in subscript, the symbol, and the left child is A naught. So for this operator, left child is A naught and right child is this T1. Then the result of this computation is T2. Next we need to perform 4 star I. So the most recent value for I is this I naught only and 4. So 4 star I is already computed. So there is no need to create the new node here. Simply we need to attach the result to this identifier list. So just we need to attach T3 with a comma. Okay. Then we need to perform B of T3. B within a square bracket T3. So T3 is a right child. So that we have to compute B0. So for this operator, B0 is the left child, right child is T3 and this is the interior node and the result is T4. So that should be attached here. Next expression is T2 star T4. So T2 is already computed, T4 is also computed. So there is no need to create a new leaf. Okay, so T2 and T4 are the left and right children for star. So the operator is star, left child is T2, right child is T4 and the result is assigned to T5. Then we need to perform P plus T5. So this T5 is the right child and left child is P. So for the operator plus left child is P, it can be represented by P naught and right child is T5. And normally this subscript 0 should be given for the leaf only. It should not be given for the interior labels. Then the result is T6. So T6 is equal to P plus T5. Then copy statement is there. P equals T6. So P equals T6 is a copy statement. So there is for copy statement there is no need to create a new labels, new node. Okay. So here T6, the previously computed T6 is assigned to P. So in the T6, in the same node itself we have to attach P. So now the current value of P is this one, not the initial value. It is recomputed. So hereafter if we want to refer P, we have to take it from this place. Then next statement is I plus 1. T7 is equal to I plus 1. I plus 1 is not computed again. So we have to consider the initial value of I. So I plus 1. So the interior node is plus. I naught is a left child, 1 is a right child. And this result is T7. Then again a copy statement, I equal to T7. So in T7 place we need to attach I as a list of attached identifier. Then the final statement is if I is less than or equal to 20, go to 1. So here operator is less than or equal to, we need to consider I as a left child. So I is recomputed now here. So we have to consider I as left child. Its operator is less than or equal to and right child is 20. So I less than or equal to 20, we have to go to 1. So that should be represented as a label here. So this is the DAG representation for this given particular example. So similarly we can construct DAG for any basic block. Thank you.